Hey everybody, it's Mrs. Dinkelman, and this is Unit 9. We're talking about exponential and logistic growth. Now, exponential growth is something you've done before, and we did a little bit last year in AB. Logistic growth is going to be a new topic for BC. So just as a recap for exponential growth, I don't know how much you remember about when we talked about this. It's kind of something generally we think about at the end of the year. But if we have something like dy dt equals ky, or dp dt equals kp, or something where the variables here and here are the same, then we know we have exponential growth, and we'll kind of prove that here in just, I think it might be in your assignment. We'll see if it's there or if I put it in the examples. And then if that k value is a positive, then you know you have exponential growth. If it's a negative, we have exponential decay. You talked about this a little bit in pre-calc for sure, and definitely in the integrated classes. A lot of times you saw it as something like PERT. That's kind of how I remember it, is that PERT right there, because PERT seems like a word, although in BC and AB you'll often see them use AE to the KT. Same thing if you want to just think of it that way. So just as kind of a reminder, again, should be review, and there's that example too where we're going to prove that that's the right thing. Find the formula for the mass that remains after t years in this particular thing. So lots of ways to do this, and you can use that 1/2 formula that you probably talked about in pre-calc, but I'm just going to go ahead and use the PERT part. So we have, first of all, that we have a y equals, the beginning is 100, e to the RT. So then they have to give us more information, so that's where this half-life is. So this will become 50 milligrams after 1,590 years. So this is how we're going to calculate what R is, so that we can then find some other answers here. So if we divide by 100, we're going to end up with a half. Surprise, because this is half-life. It's really not a surprise. Hopefully you can see that pattern happening all the time. We're going to have to natural log both sides. I'll get my calculator out here in a second, but I figure I might as well just write out exactly what I want to do. So R, and sometimes people actually just leave the R value like this, or you can calculate it. Just be careful on the AP exam for when you're rounding, because you don't really want to round to the 3 decimal places until at the end, because you don't want to miss out points for rounding errors. Okay, so natural log of a half divided by that 1590. Let's see, even that doesn't want to do it. Okay, so negative 0.000436. I'm going to just go with that, negative 0.000436. We can just grab that number off our calculator, which is really nice. Okay, so finding the mass after 1,000 years, maybe what I should do is just write my final equation that I have here. E to the negative 0.000436 t. Okay, so for this one, what we really want to do is do 100 e to the negative 0.000436 times 1,000. Okay, so we're just going to plug that in on the calculator. Okay, so we have 1,000, and then e to that number times 1,000. Okay, so 646.655. 646.655 milligrams. And then when will the mass be reduced to 30? So we have 30 equals this 100 e to the negative 0.000436 t. So we're going to divide by 100 first, so that's going to be 3/10 equals e to the negative 0.000436 t. We also have the solve feature. I'm actually not sure why I'm working so hard, but I'm going to pretend like we don't have the solve feature on the calculator. So we're going to have natural log of 3/10, and I'm going to cheat a little bit here and say we're going to have to divide that by that negative 0.000436 to isolate time. Again, we do have that solve feature on the TI-89, so we probably didn't really have to work so hard, but that's okay. It's worth it just in case. So natural log of 3/10 divided by, and then I'll go back up and grab that guy. And it looks like 2,761. I'm not going to remember all that. So this one is 2,761.55 something. 775. Just kidding. 775 years. Okay. So there's the exponential problems that normally we do. And then just to prove that that differential equation does turn into this AE to the KT, or PERT if we want to think about it that way, let's go ahead and separate here. So we're going to have dy over y equals k times dt. So when we're separating, if I haven't said this before, I try to leave as much as possible on the right-hand side. So any constants, if there was like a 2 over there, I would leave the 2 over there. It just makes your life easier, and generally that's what they do on the AP exam. Okay, so there's the separate part, integrate. So natural log of y equals kt plus c. Make sure my t actually looks like a t. Okay, e both sides here so that we get y equals e to the kt. The plus c is up in the exponent with the e. But what we're going to do here is say, well, I know about exponents. When I multiply them is when I add the exponents. And e to the c, well, e to some number is just some other number. So let's just change that to, well, our book likes to change it to an a. So there's our ae to the kt. So what you might want to do right now is go ahead and do pick through and look for the ones that are exponential. And then we're going to talk about logistic growth. So this is the new one. Logistic growth, you learn about what's called carrying capacity in probably your biology class. So what happens here generally with like disease and even rumors and other things, what happens is we have some people know it at the beginning, and then a lot of people will know it or get the disease, and then eventually we level off, and we have this kind of horizontal asymptote here. That's the carrying capacity, and that's what we're heading toward. So you'll see this differential equation looks a little bit different. We have like P for population here and a P there. So that's kind of how you're going to notice it, that it's a logistic growth. So Kp times m minus P. Now let me just say that some books and some teachers will teach logistic growth just a little bit differently, meaning their formula for the differential equation might look a little different, which is fine. We end up with the same answers. Our setups just look a little bit different. So if you are working with a tutor, or I am not your main teacher, your other teacher might have showed it to you a little bit differently. So anyhow, P is a population, M is the carrying capacity, our solution. So our original equation, if we want to find out exactly the population instead of the population or how fast it's growing, then you would need that solution. Now the A value there is not just the initial condition, it's based on the initial condition. So there's that formula there. Or I'll show you how I find it, because you know I don't like to memorize things, so I often just try to find it. I'll show you how to do that if you don't want to memorize, if you're like me. And the other thing that you need to know for the AP exam is that the population is growing the fastest, or the disease is growing the fastest at half the carrying capacity. So just kind of a by the way, when we're talking about things like COVID-19 and we're looking at graphs that way, when they're talking about flattening the curve, what they're really talking about is that rate. And so we'll talk, if you're in my class, about doing some activities with the way disease spreads and how we tried to flatten that curve and how that really does happen at half the carrying capacity. And I was looking a lot at that. Like how many more days do we think we might have based on what our carrying capacity might say? So they do this a lot. This is one of the ways scientists analyze how long they think a disease is going to take or how many people it's going to infect. You have to have really good data and really good testing for that to occur. I have a lot of Ebola data that shows us, because that disease progression, that outbreak is kind of over. So it's worth kind of looking back at it and seeing. So anyhow, that's just kind of one of the ways scientists look at it. Okay, so thinking about our growth rate here, so dp dt equals kp times m minus p. I just have some logistic questions to mention for you. So what values of p will the growth rate be closest to 0? Well, if the p, the population of whatever we're looking at, starts at 0, certainly our growth rate is going to be 0. But also when we're getting close to our carrying capacity, so if M and P are equal here, we're going to get a 0, which kind of makes sense looking back at this graph. And by the way, this graph that I showed you, I should have mentioned, where did it go, is the original equation, not the derivative. So we can see here that the slope of this as we head toward the carrying capacity is getting towards 0. Okay, so as a function, so if we look at the differential equation, just assume it's its own function where P is the x value. It's an upside down parabola, and that's because if we simplify here, we're going to have km p minus p squared. Again, p is the variable there, and so it's an upside down parabola. So how are we going to find the vertex? Well, I think the easiest way to find the vertex is probably to look at y prime. Just find the min or max. So km minus 2p, and where that's 0, then we'll know, again, it's an upside down parabola, we'll know we're talking about that spot right there. So that's where km, I don't know why I have km in there. Hopefully you were going to tell me that that derivative is not right. Nope, it is good. Okay, so km equals 2p. There's a k here. There we go. That's what I'm missing. There's a k there. So km equals 2kp, because there's k's on both sides, we can just get rid of that. And so basically at half the carrying capacity. So that's that thing I told you earlier about how it's growing the fastest at half the carrying capacity, because we find this maximum at half of that and for that parabola. Describe where the max rate occurs. So that's exactly it, half the carrying capacity. If the initial population is less than the carrying capacity, we're going to have that positive growth rate. If we start above the carrying capacity for some reason, it's going to, we're going to kind of come below, we're going to be decreasing in population. And if we're equal to the carrying capacity, we should have really nice, steady, just almost a 0 there. Lots of questions that are going to ask us about logistic equations. So lots of different ways to do this. So this one is already in that form, Kp times m minus p. So what's the carrying capacity? It's just 100. What is the var population when it's growing the fastest? Well, it should be half of that. And what is the rate of change when it's growing the fastest? So what they're really asking us to do is to go ahead and plug in that population. So that times 50, and then 100 minus 50 is what they want us to calculate. So let's go ahead and do that. So I'm just going to do 50 squared there. So it's going to be 20. So it's growing, let's see, what is this about? Bears, it's growing at 20 bears per, they didn't really give us a time period there. So 20 bears per whatever they were measuring. For example 4 here, we're looking at a tank full of guppies, so carrying capacity is forced, which sometimes happens, although sometimes it skews our data a little bit if we're looking at it scientifically. So 150 guppies, 6 are introduced, so that's going to help us figure out our A value, and then they give us the growth rate, and luckily it's in the Kp times m minus p, and we can see that carrying capacity there, so they didn't really need to tell us. So we're looking at trying to figure out what the original equation is. I'm talking about the P equals m over 1 plus a e to the negative mkt. So for this one, so far what we know is that, see, that's a 150. We don't know a yet. We're going to find k and a here. So let's go ahead and find the A value first. That's based on the initial condition. So I'm going to use this 6 guppies. So the population is 6. When time is 0, so all of this is going to become 0. And remember, e to the 0 is 1. So from there, I'm just going to kind of do like a cross product here. So 6 plus 6a is 150. So 6a is 144. So a is, I believe that's 24. Now, let me scroll up really quick just to remind you that earlier I told you there is a formula for A if you want to memorize it, and here I have it, I've written it already. What we just did is we took our carrying capacity and subtracted our initial population, which was 6, and so we end up doing the same thing that way. It's just whether or not you want to have it memorized or you just want to mathematically find it every time, so that's totally up to you. Okay, so let's put that bit of information in. And actually, we'll go ahead and put in, we should have known the k earlier, which we could have put in. So this is 1 plus 24 e to the, and so this right here is our k value times the 150 for mk. So let's see. 0.0015 times the 150 carrying capacity is negative 0.225, so negative 0.225 T. Okay, so then we can answer this question, how long will it take it for it to be 100? So let's go ahead and just use the solve feature here just to make our life easier and maybe for me to remind you about how to solve. So F2 algebra, we have solve, and we want this thing to equal 100. So 100 equals 150 divided by 1 plus 24 e to the negative 5t. Okay, make sure I get the right number of parentheses there, tell it what variable I want it to solve for, and then we'll be good. So t is 17.205. 17.205, and let's see, weeks. Earlier it told us that t was in weeks. So maybe just try to think of some places where we might want to use exponential or logistic, and honestly some of them could be the same situations. It just depends on the time frame or what we're looking at. So go ahead and get started on the assignment, or finish if you've already started the exponential growth.